When does a derivative not exist? If there is no single tangent line through a point, then there is no derivative at that point. One might wonder if the derivative does not exist or if it is undefined. On one hand, if the derivative relates to a point of discontinuity, such as a function being undefined, or an undefined slope, the derivative might be undefined. On the other hand, a derivative is defined as a limit, and if a limit does not exist, the derivative does not exist. For simplicity, we will say the derivative does not exist, but this is a very interesting conversation. Let's consider the case where a function has a cusp. This function f of x equals absolute value of x, and it has a cusp when x equals 0, which means it has a sharp corner. We could think of this function as a piecewise function. It can be written as positive x if x is greater than or equal to 0, and negative x if x is less than 0. And let's approach the cusp from the right and from the left. If we're approaching from the right of 0, we're coming in the direction of a slope of positive 1, and you could think of that as the derivative of positive x being positive 1. If we approach 0 from the left, we're coming from a slope of negative 1, and you could think of that as the derivative of negative x being negative 1. We can draw infinitely many other slopes through a cusp. This would be a potential slope, and this could be another potential slope. So there's not any one single slope that we could draw through a cusp. Any of these slopes are possible. Since we do not have one particular slope at 0, we would say the derivative or the slope at 0 does not exist. What about an undefined slope? This function f of x is cube root x, which we can write as x to the 1/3 power. Calculating its derivative, f prime of x, applying the power rule would give us 1/3 x to the negative 2/3. And we can rewrite this with the x term in the denominator using the negative exponent rule, 1/3 multiplied by cube root of x squared. This derivative is undefined when x equals 0. So f prime of 0 is undefined, and we could think of it as the derivative does not exist, but it's because the slope is undefined. Let's see what the slope would look like. If we drew the slope at 0, it would be a vertical line, making a tangent line to that graph, and then a vertical line has an undefined slope. Since the slope is undefined, we're going to say, for simplicity, the derivative does not exist. We need a function to be continuous for it to be able to have a derivative. Continuity is a necessary but not sufficient condition to prove that a derivative exists at a value, so we need a function to be continuous. So let's look at what's going on when the function is not continuous. We have a removable type of discontinuity when x equals 3. The limit exists at x equals 3. If we approach from the left and from the right, our limit is approaching negative 1 from each side. However, the function value does not exist at that same limit value, and we cannot draw a tangent line through that point. So we would say the derivative does not exist. We have a jump discontinuity when x equals 1. And if we take the limit as x approaches 1 from the left, we're heading to 3, and from the right, we're heading to negative 1. So those two one-sided limits do not exist. Or since those two one-sided limits are not equal, the limit does not exist. When the limit does not exist, the derivative does not exist. And thirdly, we have an infinite discontinuity when x equals 4. The limit is infinite, since as we approach 4 from the right, the function is approaching positive infinity, and similarly it goes to negative infinity to the left. So we cannot draw a tangent line through this, and we have an infinite limit. The limit doesn't exist by that definition, so the derivative does not exist. So all three of these conditions, we cannot draw tangent lines through these points. But let's take a look at where the point x equals 5 is continuous. So we do have a continuous value when x equals 5. That means we can draw a tangent line, and if we draw a tangent line crossing through that point only once, we would use that to approximate the derivative at x equals 5, which is the slope value when x equals 5. So that's the only point we considered where that function is continuous and it has that derivative. Also important to note, because there's no cusp at 5, that's why the derivative exists at 5 and it is continuous.